So the next step is to move into the inverse kinematics, which is a little bit more difficult, and it is the more useful calculation. If I know where I want to move, I want my x, y, and z to be, which we would put into these boxes as a change based off of where it's currently at. That will output for us what joints 1, 2, 3, 4, 5, and 6, what those joint angles should be. So we're going to start out with just talking about the x, y, and z for now, and how that transforms x, y, and z into what joint 1, 2, and 3 should be. So this is done pretty much geometrically. It's not too difficult actually. It gets a little bit busy. So each of these pictures that I have in here show a different arm configuration. So we'll start with that. So of course it's going to be, so move somewhere where it's not on the bottom. So this is kind of a wireframe version looking at our robot. If I'm looking straight down at my robot in this picture, I can see here's the center of J1. And if my robot is over at point P, then it's pretty easy to do some basic math to figure out what J1's angle should be. I can just use Pythagorean theorem, use X, use Y of my position. So J1, that one's super easy to get. I can get that pretty much no problem. Getting joints 2 and 3 is a little bit more difficult. I have to do some similar math, but now we're going to look at the wireframe model of the robot from the side. So if this is point P out here, then given that position where that's at, I should, doing this from this math equation earlier, we know that the x value is this arm length here, and then we can then try to figure out, use various equations to figure out each of these different triangles. Now I could probably spend a lot of hours sitting here going through every one of these formulas, but I'm gonna kind of breeze through this and just kind of touch on it, because you can come open up this Excel spreadsheet and you can look at each one of these. I have them all labeled so they match what's in the pictures here, and you can see how each one of these angles is calculated to come up with each of them. But before we get into any of this and just touch on any of this, I wanted to go through each one of these pictures, because what I'm getting at here is that there are different arm configurations. The math changes based on where the arm is. So this is arm forward. With this model that I came up with, this is with axis 3, and basically the elbow and the wrist are out forward in front of the robot. So that's the forward configuration. That's the model for that. The next one that we have here, let me blow this one up. So this one is arm in the mid position. So again, it's a similar calculation here. It changes a little bit with arm in the mid position, but you can see how now joint 3 is, let me back up. The point, the center point of the robot is now behind J2. So you can see that straight line coming down. So in this arm mid configuration, that's the problem, is that P is now behind J2. So that makes the math for finding all these different angles a little bit different. So that's the arm mid configuration. And then over here, this is the arm back configuration that I came up with. And again, finding J1 is similar, so it's a little bit different, just that you're going to find the X and Y over on this side this time. And then with the arm back, you've got P and J3 are now behind J1. So now I've got a bunch of different triangles that I have to solve for. So you can see they're all marked here with theta 6, theta 2, D7, D8, J3. So you can look at these wireframe models, and then you can dig through all the math that I've done here given that they're all labeled the same as the picture, and you can see how the math was done. And one thing to consider here is these are just 3 arm configurations. What I did not do is I did not do an elbow back configuration. I didn't want to go to the trouble, and I've never had a need to run the elbow back. But the elbow back configuration is if you were to take J3 and bend it backwards like that. I've never really had a need to do that. And that was a lot more complexity into the math, and I was just trying to get it so it was working and I could figure it out. So there is no arm back configuration, and you'll see that in my program that the limit on J3 is +1. I don't let it go to 0. 0 is a no-no, and without doing some other calculations. So we got 1 degree all the way down to +140. So this 1 to 140 is kind of a reflection of the fact that I didn't do an arm back configuration in my robot. The other thing to consider is that there's another value that we need to know is the quadrants that the robot is in. So over here, let me go up, find it. So these quadrants for J1, J5. So this quadrant basically calculates either I think quadrants of 1 or 3 based off of, let's see here, excuse me, actually it's, here, let me back out of there. So these quadrants is the way I split up to be able to tell where the tool center point was in. So I have quadrants 1, 2, 3, and 4 for J1. That's how I tell which way the robot's pointed, whether the value is negative or positive for the J1 axis. So for example, if my degrees are at, let's say, +5, I'm in quadrant 3. If I go to 95, I'm in quadrant 4. So if the world we live in, this is quadrant 3 for the robot, this is quadrant 4 for the robot, assuming that, let me center that, assuming that this square here that I'm drawing, let's pretend that's the world that the robot lives in, and the very center is the center of the robot. When the robot arm swings over into this quadrant, that gives it quadrant 3. When the robot arm swings over into this quadrant, it's 4. Now if I went, say, -5, I'm quadrant 2. And then if I go -95, I get back into quadrant 1. So I'm using this value right here to kind of tell me for my inverse kinematics of where the robot's at, of what quadrant the robot's in. So if I looked at this from above here, basically that would be quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So that's how that's used in the calculation, and basically I just came up with some if-then statements based on the XY position and whether it's negative or positive. You can see that formula right here. It's pretty basic. Excel if-then statements are horrid to deal with, but once you figure them out, you can see what's going on. But basically it just sets the value based on some if statements based on if the x and y of J1 is negative or positive, and figures out what quadrant it's in. And then this quadrant here for J5, this is trying to find the tool center point, what quadrant that it's in. So you can open up and you can see that if-then statement, and it looks at the XY values, and again negative, positive, and tries to figure out which quadrant that the wrist is in. And I use these quadrants, the quadrants for J1 on this model here. The quadrants for J1 are applied to the formula to find out, if this is what this angle is, if it's negative or positive. And then the quadrants for J5, that's what I'm using to calculate whether it's arm forward, arm mid, or arm back. So I'm kind of just slowly breaking it down. I use a few basic things in the forward kinematics to figure out where the robot's at. So you kind of have to run the forward kinematics first, and then you run the inverse kinematics, because you kind of need some of these, you need to know a few of these things before you run the inverse kinematics. So I'm using those quadrants against these wireframe models to do the math that is in this red box here. So this red box is going to tell us the value for J1 is going to come here, the value for J2 is going to come here, and the value for J3 is going to come right there. So if we look at the math here, the radians for J1, we're basically we just get the xy, and then through this long series of if-then statements we just do Pythagorean theorem and figure out what the degrees are for J1 based on what quadrant we're in. So J1 is pretty easy. So you can look at these two calculations here and see how they're being applied to each of these models based on which quadrant it's in to see how we're getting J1. J2 gets a little trickier. You can step through here and see all the x arm lengths, the y, the d7, and you can look through all of these and see how each of these are being applied. But it's basically just using basic geometry, Pythagorean theorem, and then calculating through until we finally go through a series of if-then statements that are rather painful to figure out, which configuration we're in and which angles to use, which gives us the value for J2. And I know I'm not going into a lot of detail here, but it would take a really long time to go through all this, and I think it's pretty basic geometry, so it's nothing you couldn't figure out by sitting here looking through it. And then the same thing with J3, just uses the a cosine function to you can see the formulas up here based on those angles to get J3. So again, just to recap, the output for joint 1, 2, and 3 is just based off of basic geometry, given a few quadrants and angles, Pythagorean theorem, figuring out triangles. It's just a lot of figuring out triangles to get those values for joints 1, 2, and 3.